Hi everyone, today we have a few 2D kinematics problems for AP Physics 1. The AP is coming up soon, so let's get started. Question 1. A cannonball is fired from ground level at a speed of 90 meters per second at an angle of 40 degrees above the horizontal. It eventually hits a vertical wall located 300 meters away. Question A. How long is the cannonball in the air before hitting the wall? Okay, let's draw this out first. So our cannon firing a cannonball at 90 meters per second at an angle of 40 degrees above the horizontal that eventually hits a wall that is 300 meters away. Okay, we can also make an XY chart to summarize some of our variables at play. The acceleration in the x direction is 0 because it is only given an initial velocity, but in the y direction it is negative 9.8 meters per second squared because gravity is acting on the ball throughout its entire trajectory. For the initial velocity in the x direction, we have VO cos theta, and for the initial velocity in the y direction, we have VO sine theta. Okay, so for question A, we want to find how long it's in the air before it hits the wall. We can use our distance equation for x. So dx equals v naught x t plus 1/2 a t squared. Before we plug in, we can get rid of 1/2 a t squared because there's no acceleration in the x direction. So we end up with dx equals v naught x t. And now we can plug in. The cannon is 300 meters away from the wall, and we're given an initial velocity v naught cos theta t, v naught being 90 meters per second, and cos 40 degrees times t. So isolating t, we get 300 over 90 cos 40, which when we put into our calculator is equal to 4.35 seconds. Part B asks for how high above the ground does a cannonball strike the wall. So we're looking for D at wall, dy at the wall. We can simply use our dy equation and plug in our time that we got in part A, because at 4.35 seconds the ball has hit the wall. So we can plug in. V naught y becomes V naught sine theta t plus 1/2 a t squared, which is equal to our initial velocity of 90 times sine 40 times the 4.35 we got in part A plus 1/2 negative 9.8, as the acceleration works in the opposite direction as our initial y velocity, times 4.35 squared. And when you put into your calculator, it is equal to 158.93 meters. For problem 2, we're given a trajectory of a ball and a few points labeled on its path. At which points is the projectile speed the greatest? If we're trying to find the speed, we have to consider the velocity and the x and y components. The velocity in the x direction is constant throughout the entire path because there are no forces working in the x direction. However, for the velocity in the y direction, we have to consider the initial velocity in the y direction as well as gravity, which is negative 9.8 meters per second, assuming we consider the positive direction as up. Points A and E have the greatest speed because at point A, there is an initial y velocity, and as soon as the ball is fired, gravity works down on it, slowing it down in the y direction. And once it hits point C, gravity works downwards on the ball, speeding it up until it hits the ground. We can also reason that with the conservation of energy, assuming that points A and E are on the same y level, the kinetic energy of the ball at point A will turn into potential energy at C and then return to its full amount of kinetic energy at point E. So points A and E. Part B asks, at which point is the speed the smallest? This would be point C, because at point C, the ball has reached its peak and only has velocity in the x direction. And part C asks, is the acceleration the same at all points on the path? And it is, because regardless of the speed of the ball in either the x or y direction, gravity acts on it with the same magnitude throughout its entire path. Water flows horizontally off the edge of a cliff at a speed of 15 meters per second, falling from a height of 200 meters into a river below. What is the speed of the water when it hits the river? Let's draw this out. We have our cliff that is 200 meters tall, with water flowing off the edge and hitting the pool below with an initial x velocity of 15 meters per second. Let's assign the positive direction as down. Let's draw an xy table to see our components. There's no acceleration in the x direction, but gravity works downwards on the water. V naught x is 15 meters per second, but there's no initial y velocity. And we're looking for V final in the x direction, as well as V final in the y direction. Part A asks us the final velocity when it hits the water. We can redraw the water hitting the river and analyzing the x and y components. It has some final velocity y and some final velocity x. And we are looking for the sum of these vectors, which is also the hypotenuse of a triangle we just drew. So we can say VF is equal to the square root of VFY squared plus VFX squared. We know that VFX is 15 meters per second because the initial velocity in the x direction is 15 and there's no acceleration, so the velocity will stay the same. But for VFY, we need to use one of our kinematics equations. We can use VFY squared equals V naught y squared plus 2AD. If we take the square root of both sides, we get VFY equals the square root of VOY squared plus 2AD. And now it's a matter of plugging in. We can say VOY is 0 because there's only direction in the x component when the water starts to fly off the cliff. So this is equal to the square root of 2 times 9.8 times 200, which when we put into our calculator is equal to 62.61 meters per second. Now if we plug that in for VF, we get 15 squared plus 62.61 squared, which is equal to 64.38 meters per second. Part B asks for the angle that the water strikes the river surface. If we go back to our model here and extend some of our vectors, we have the two vertical angles here, and we can use theta and our velocity in the y and x components to find the angle. And we can see that tan theta, which is equal to the opposite side over the adjacent side, is also Vx over Vy. So let's move that down here. and solve for theta. Theta is equal to inverse tan Vx over Vy, which is also equal to 15 over 62.61, which is 13.47 degrees from the vertical. Thank you for watching.